Thank you for the warm and awesome welcome. So yeah, I'm Dario, and I will be talking about Embassy. So for a bit of background, like how did I end up here? Who is this guy? So I'm the CTO of Achilles, my company where we do smart access control systems. So it's a suite of devices with different capabilities for access control. So we manufacture, design, and test, and then sell the hardware all in-house. And as part of this process, we had, of course, to write the firmware for them. So at the very beginning, I wrote the firmware in C, using the tools from the vendor SDK. It worked. It was enough to launch. The devices worked well enough to get paying customers. But as the project scaled up in complexity, we wanted to do like more things concurrently, add new networking protocols, expand the capabilities of the devices. I found C was starting to become a nuisance. So this was 2019. Async Rust had just been stabilized. Like Rust had been on my radar for a few years. And like async Rust was like the trigger. Like I was wondering, hey, maybe this could be great. So in 2019, 2020, I actually did the crazy thing of rewriting everything in Rust using async. And as part of that process, I started writing some tools like an executor suitable for embedded systems, and then hardware abstraction layers for using the chips we were using, and then other chips. Posted it on GitHub. It started getting some traction. So this is what's now known as the Embassy project. So I'm also now the maintainer of it, main maintainer. So when I say async for embedded systems, like embedded is a very wide term. I'm focusing mainly on microcontroller-based embedded systems, like not embedded Linux, like routers or kiosks, but just microcontrollers. So these are really small chips, commonly using architectures like ARM M profile, so it's more restricted than the ARMs on your phone or RISC-V, other architectures. They come with no OS. Like from the moment you apply power to the chip, the first instruction that runs is your code already, unless of course you can bring your own. More on that later. They are tiny, like a small microcontroller would be like 4 kilobytes of RAM. They go up to 256K, would be considered a big one, and 1 megabyte of flash. And also this is interesting, since you typically have solid memory, it's the best practice to not use alloc, to not use a heap. It's not actually required. There are crates you can add to your project to get a working heap, and it integrates with the standard library, so you can get vec and string and all the maps working. But since you have solid RAM, it makes RAM usage actually very unpredictable. Like you don't want to like receive a big string over the network and then run out of RAM in like a random place in your code. That's like impossible to handle the error. So basically all you can do is like crash and reboot. So to avoid this, you typically avoid using alloc. Like you use fixed size buffers. If you know you need to handle 3 connections, then you create 3 connection slots, etc. So when you write firmware for a microcontroller, in C, traditionally, you would use an RTOS, a real-time operating system. There's many of them. This is by no means an exhaustive list. There's a Wikipedia list, which is really intimidating. There's hundreds of them. Because as soon as you want to do like moderately complex things, like handle data on a TCP connection at the same time you wait for button press, at the same time you handle Bluetooth, like if you have no OS, you have no threads, you have to make one main loop handling everything and write everything as a state machine manually, which is really annoying, scales really badly and composes really badly. So you would use an RTOS. It gives you threads, which is commonly called tasks in RTOSes, which actually has nothing to do with async tasks. It's the same as threads in Linux. So each thread has its own stack, its own CPU registers, and there's like a tiny kernel that does context switching and scheduling between threads. You get all the usual niceties to use threads, semaphores, media access channels, mailboxes, whatever. You get drivers for your microcontroller. So if you have a serial port, you want to do some I/O, that typically comes as part of the RTOS. So you write on top of the RTOS APIs to do I/O, and that uses the drivers for your chip underneath. And for more complete RTOSes, depending on your use case, you may want to get a network stack, a file system, key value store, whatever. So in 2019, and it has improved a bit today, but I would still say this is the case. There was no mature RTOS in pure Rust back then. There were a few like Tok, but like for more niche use cases that didn't apply to the things I wanted. So I had the option to either use no RTOS, but that wasn't very appealing. I had the option of use a wrapper for a C RTOS, but that's not very appealing either. If you have to bind gen, it comes with its own set of problems, and you have to juggle the C compiler and the Rust compiler. So if you can avoid that, I would recommend you avoid it. So I thought, hey, there's Rust, there's this thing called Async, just stabilized with a quite unique design, like this thing that converts straight line code to state machines for you, and the state machines are like completely sized at compile time, so it could work without alloc. So even if the underlying mechanism is very different to RTOS threads, maybe this could give you like a similar developer experience. Like you got tasks where you write straight line code that each task handles one thing, and you got like a scheduler, in this case it would be the executor, that makes sure all these tasks get scheduled and run concurrently. So I wonder, hey, let's give this a try. So to begin with, the most critical piece of using async is the executor. So this is a rough overview of how a standard executor in Linux would work, like Small or Tokio. So first of all, you allocate all the tasks in the heap. Each task contains the future, that is like the top level future for the task, plus a bit of bookkeeping data. You got wakers that point into these tasks. You got the executor, which has a task queue of all the tasks that have been woken and are pending to be pulled. All of these have pointers into the heap. You can have multiple pointers into the same task, so you need to reference count them. So each waker counts as a ref count. Each time the task is pointed from the task queue, that counts as one ref count. All the other things like join handles and stuff like that also points into tasks, also counts into a ref count. So when the ref count reaches 0, you can deallocate the task. Like when it exits and there's no wakers pointing to it, you can reclaim that memory and then reuse it later. And all these tasks, when pulled, they register their file descriptors into something commonly called a reactor, which is usually driven as part of the executor. The reactor collects all the file handles and then tells the OS, hey, I've pulled all these tasks, they're waiting on all these file descriptors, and then you do a single system call saying, hey, please notify me when one of these file descriptors becomes ready. So the main loop of the executor looks something like this. So this obviously doesn't work in embedded. First of all, it uses alloc. We have to get creative to try to get it use no-alloc. And second of all, we have no operating system. We don't even have a concept of file descriptor. So we don't have EPOL. How do we make this work? So this is the main structure of this talk. I will be going through all these challenges, and we will explore how Embassy solved them, what similarities and differences are there between Embassy and a standard async executor. So first of all, let's get rid of alloc. So obviously, you cannot allocate the tasks in the heap, but also there are also other uses of alloc in the executor. For example, your task queue could be a vec or a dequeue that, since it can hold an amount of tasks that you don't know at compile time, it has to grow dynamically, so that uses alloc also, so we cannot use that either. We have to use different data structures. So where do we allocate the tasks? So in a Rust program, there's only 3 main places you can allocate things. You can allocate them on the heap, on the stack, or on statically, on a static. So of course, we cannot heap allocate them. We cannot stack allocate them either, because wakers have no lifetime attached. They can live forever as long as the user wants to. And we have to prevent waker pointers from becoming dangling. So with a reference count, you can actually delay deallocating the task until all the wakers are gone. But in the stack, you cannot do that because the user can return from a stack frame at any time, and the whole stack frame will be deallocated, and that will leave dangling pointers in the wakers. So that's not a possibility. So the logical conclusion is third place, and the only alternative left is statically allocate them in a static. So this is what Embassy Executor does. Each task gets its own static variable with a task structure. That same idea. It wraps the task's top-level feature with some extra bookkeeping data. And for the task queue, instead of using a dynamically sized queue, we use an intrusive linked list. Because it's even if Rust is not great at linked lists, you have to use someone safe. But the good thing about it is you don't need dynamically sized data structures. Like every task you allocate has room for one pointer for the next task, and then the executor has a pointer into the first task. And then wakers, of course, just point into the tasks, and you don't need to do any ref counting at all. Like, since tasks are statically allocated, they live forever, so all these pointers are valid forever. So waker drop is a no-op even. So this actually simplifies the executor a lot. So to statically allocate tasks, this is how a small Embassy program would look like. As you can see, it looks almost the same as a standard Rust async in like you would write in Tokio. You write an async function and then you spawn it. The only difference is this thing here. We got a macro saying, hey, this is a task. This is not a regular async function. This is a task. And you need this because you need to create a static for each task. And the only way to do this is with a macro if you don't want the user to write this manually. So this expands to a static containing the task, then the async function, which is renamed with an inner suffix, so the user doesn't touch that directly, and then the function that the user does call initializes the task in this static, and then returns something called the spawn token. So instead of returning the actual future, it returns the spawn token, which is kind of a pointer into a task that's been initialized and is ready for start to run. Because like we cannot actually pass the future to the allocator like you would in std, because the executor would have to heap allocate it. So one challenge with this is in Rust, maybe you've run into this if you have used async. The return value of an async function is the future for it. And it is actually a struct auto-generated by the compiler, like this automatically generated state machine. It implements the future trait, but the actual type of it is a magic type that's not nameable. And in Rust, there is no type inference in statics. So you have to name the full type of the task future in the static. So how do you do this is using nightly only features, type alias input trait. So you can say, hey, I have this type alias called my task future, which is input future. It's some type that implements future. I will leave you to the compiler to figure out what it is. And it's kind of some whole program type inference. So it will look at all the usages of that type. And when you equate that type with the actual future type returned by my task inner, it will actually infer, hey, this type is this future. So this way you can give a name to this magic unnameable future type, and then you can just use it in the static declaration. So of course the challenge is this is nightly only. So currently Embassy works on stable, but it has a fallback which uses a very simple bump allocator. So you do have out-of-memory errors at runtime, but only when you spawn tasks, which you typically do only at boot. And only if you use nightly, you can opt in to be fully no-alloc. But yeah, this is something that should get stabilized eventually. And when that happens, Embassy will be truly no-alloc. And the second challenge is we got no operating system at all, as I said before. So how do we do I/O? Well, a very rough overview of how I/O works on a microcontroller. these things are actually called system on chips. They're not just the CPU core. They're a set of things, among which there's the core, which is actually what runs your code. It's connected to a data bus, and through that data bus, it can do memory transfers to flash, RAM, and also to peripherals. These peripherals are connected to the pins, the physical pins on the chip, and you would connect them on your board to like buttons, LEDs, motors, sensors, whatever you want your device to do. So to talk with these things outside your chip, you need to use these peripherals. So how do you use a peripheral? Well, the peripherals are memory mapped, so you use MMIO, memory mapped IO typically, which means like the peripheral appears in some magic region of memory, which is neither RAM nor flash. Instead, it has like registers, which are like magic memory locations where like you can do a write to tell the peripheral to do things, or you can do a read to receive information from the peripheral. So for example, imagine you connected a button to a GPIO pin. You could say, hey, pin config, write direction input. So you tell the peripheral, hey, configure this pin as an input because I want to read from it. And then you can read the input register, and the peripheral will tell you, hey, the pin is low, so the button is not pressed, or the pin is high, so the button is pressed. So this is the basics of how you do I/O. But you not always want to read the state of something. You sometimes want to wait for something. For example, we want to wait for the button to be pressed, which is a really common thing to do. Typically, if your device has some kind of UI, you sit idle and you wait for the user to press a button or touch something in the touchscreen. Or a sensor to detect something. So the dumb way to do this is, okay, fine, I will spin, read this register in a loop, and wait for the value to change. So when it goes high, hey, the button has been pressed, and then break the loop and continue. But of course, this sucks for a few reasons. First reason is, while you're spinning here, you cannot do any useful work. You're just waiting, burning CPU time. And of course, it's also really bad for low power. If you build battery devices, battery-powered devices, which I do, you don't want to do this because you're like keeping your core on all the time. Well, if you would do something smarter, if there's nothing else to do, you could put the core to sleep, saving a lot of power. So to solve this, peripherals also have this thing called interrupts, which is an extra signal from the peripheral to the core, where the peripheral can say, hey, something happened. And then when a peripheral fires an interrupt, the core will magically say, oh, something happened. It will magically stop executing wherever it was executing it. It will interrupt execution, that's hence the name, interrupt. And it will jump to an interrupt handler, which is this function at the top with this interrupt attribute. So as you can see, this function is never called. And this is not because the example is abbreviated. This function is really never called from the rest of your code. It's called by the hardware. It's like a callback that the peripheral sends you. So for example, you can tell the GPIO peripheral, hey, write the sense field to high. Like, hey, wait for this pin to go high. Send me an interrupt when it goes high. And then once you've done this, you can go do other things, or you can go sleep, and the peripheral will send you an interrupt. And then when you receive this interrupt, you can check the event, check what happened, and say, hey, the button was pressed. So we get the same functionality as before, but it's much more power efficient, much more CPU time efficient. So this is the core of how I/O works on a microcontroller. Like all peripherals are a version of this. They might be more or less complicated, but the idea is this. You wait for interrupts. So let's asyncify it. Let's actually wrap it into Rust async to make this actually easy to use instead of getting interrupt callback hell. So how do you do this is write a feature. So at the very bottom level, when you're interacting with the hardware, you will have to write features manually instead of using async fun. So what you do is, the first thing you do is you register the waker on a global variable. And then you check the pin. Is it high? Is it low? Is the button pressed or not? If it is, then great, we're done waiting. Return ready. And then the caller will keep executing async code that was after it. If it's not, return poll pending. That will signal the task to yield, saying, hey, I'm waiting for something, I cannot do any more progress. And since we registered the waker in a global variable, the interrupt will fire, And when the interrupt fires, you wake the waker, which will put back the task into the executor's queue. It will get polled again. This time we will go into the ready branch, and then execution will resume. So once you've stood up all this infrastructure for peripherals, using async is really easy. You just await things, and you can use all the classic combinators and timeouts, join, select, whatever. So this is a bit of an overview of the main loop in embedded async. So it's not driven by epoll, it's driven by interrupts. So you got the tasks that poll futures. The bottom leaf futures will wait for events from the hardware, so they enable the interrupts to tell the hardware, hey, please send me an interrupt when the event happens. And the interrupts will wake the task, which will cause polling again. And so this will go on and on and on, and this is what drives execution forward. So one very interesting difference between this and desktop async is there's no reactor. Like, you might have noticed here, this is the entire implementation of the driver. There's nothing that talks to the executor saying, hey, please register this file descriptor, or hey, please wait for this interrupt. The driver is completely self-contained. It registers the interrupt handler and enables it and talks to the hardware all on its own. It doesn't need anything from the executor. So the executor is just polling tasks and then sleeping the core. So one really cool side benefit of it that I found quite surprising, because I was hoping this to be worse in embedded than in non-embedded, but actually it's the other way, interestingly, is you don't get this fragmentation that you get in standard executors like Tokio, where if you use Tokio TCP IO, that needs to register a file descriptor in the Tokio reactor, and then you must be running the Tokio executor for that to work. Otherwise, it just won't. So this is not the case in embedded. You write drivers, they work, and they work with any executor. And as long as you write your executor properly, it will be able to run any driver without having to explicitly add support for particular hardware to it. Like, it's almost architecture independent even. Like, if you want the executor to put the core to sleep, you have to do some architecture-specific things, but that's about it. And we got our goal of replacing an RTOS. So async is not an RTOS, but it gives you the convenience of one. So you can use it instead of an RTOS, not on top of it. We're not like getting POSIX APIs from an RTOS with epoll or select and then laying async on top of it. So the advantage is it's fast. It's about as fast as using an RTOS. Like, the latency from wakes and scheduling is pretty much the same. Code size is smaller. The executor is just like 600 bytes, while for an RTOS, kernel that does context switching would be bigger. And also it's kind of simpler because you're not using lower level things from the architecture for doing all the context switching. So to finish, this is actually not perfect. There is one big hole in Rust today that is causing problems for embedded usage, which is DMA. So when you read some data from a peripheral, if you want to read byte by byte, you will get an interrupt for every byte, which is really inefficient. So what you do instead is you tell the peripheral, hey, here's a pointer, please receive 256 bytes to this RAM location. And the peripheral will do all the receiving there. It will write the data for RAM to you. And then it will only send an interrupt at the very end when all the receiving is done. So it's much more efficient. And it's also more ergonomic. You just do a read on a borrowed buffer. It's transparently using DMA underneath. It combines perfectly with all the async combinators. So for example, with a timeout, if you drop the read feature, it will go and tell the DMA, hey, please stop reading. I'm getting aborted. Please, that buffer is no longer yours. Just stop. But the problem is, in Rust, you don't have guaranteed that drop is called. You can leak things. So you can create a feature that borrows a buffer, start DMA, and then forget the future. It will prevent drop from running, but it won't stop the MA. The MA will keep writing to that buffer, which is no longer borrowed. And you can, like, for example, return to the allocated, and then that buffer will be reused for something else, causing undefined behavior. And the truth is, Rust has no good solution for this today. Like, I've tried everything. Embassy's current position is just please don't. So it's a bit unfortunate that we still have a bit of like C thing that, hey, you're holding it wrong. So it's actually the same problem as in IO U-ring. So IO U-ring solves it by using owned buffers like vec, but we can't because no-alloc. Using static inline buffers causes a lot of bloat. Static buffers is not really ergonomic. So Rust really needs a solution for this. So there's been a lot of conversation about this in the past years, either some auto-trait leak, forgettable, or must move, like undroppable types or unforgettable types. So we really need something like this, because otherwise there's no way we're going to get safe and ergonomic embedded DMA libs or IO U-ring libs that have no overhead. So to finish, a rough overview of the Embassy project status. We have the executor, we get also real-time preemption, you get all the utilities you would expect from an async runtime, join, select, channels, mutexes, timers, instant and duration. It's got a built-in network stack where you can do async IO, USB stack, Bluetooth, and then within the Embassy project, we maintain hardware section layers, like collections of drivers for doing IO, for Nordic NRF, STM32, and Raspberry Pi RP2040 microcontrollers. But actually, as I said before, you can also choose to just use Embassy Executor and then use another hardware abstraction layer. For example, Expressive ESP HAL, shout out to them. It has really great async support. So current status is it's mostly mature. It works really well. It has allowed us to ship really working, really stable firmware with lots of like fancy networking things, Bluetooth, Ethernet, Wi-Fi, mobile, mesh networking, and also low power. Like async is really great because it gives you like low power operation for free. Like we get battery powered devices that where the battery lasts for 1 year without actually having to do any special things in your code. Like just yield and wait, and the executor automatically puts the core to sleep, and you get the best power consumption possible. So yeah, that's it. Feel free to reach out. Feel free to check out Embassy. If you have any questions, just ask. Thank you.
Thank you, Dario. Thank you. Right, so are there any questions for Dario? Oh, there's one.
Wait. So one nice thing about RTOS is the ability to have hard deadlines. How would that work with Embassy?
Yeah, so I've glossed a bit about it, briefly mentioned it here. Async is purely cooperative. So if you have two tasks and then one task wants to run, for example, it's got an interrupt, and another task is running, it will have to wait for this task to finish. However, this is only within one single executor, and then Embassy layers on top of this a real-time layer where you can create multiple executors at different priorities, and executors at higher priorities are driven by interrupts. So if a task on a higher priority is woken, it will trigger an interrupt, which will trigger the higher priority executor to start pulling it, preempting whatever task was at the lower priority. So yes, you can get real-time preemption, kind of like in RTOS. You pay a bit of latency for the executor in the higher priority, but it's mostly constant time unless you do like really egregious things. So yeah, you can do real-time stuff with it. If you really cannot pay the overhead, you can of course choose to use raw interrupts, and you can even mix in the same program raw interrupts and async for the less higher priority things. Yeah.
Someone online is asking, are there any production-ready projects written in Embassy so they can check it out?
So they tend to be mostly closed source because it's people using it for their companies. There's an embassy in the wild section in the documentation. It lists some open source projects like sensor platforms, keyboards. I don't know of any like commercial grade project which is open source. Like mine isn't, for example, sadly.
Yeah, so in normal async await, you know that your code will only yield, I don't know, wait point. But if you're using interrupts, I guess, well, your code can be interrupted at any moment. Does that have any consequences for the way you program your application?
Yes, very good question. So within the executor, everything is cooperative, and the executor is kind of single-threaded. So tasks running in the executor don't need send sync, like for example in multi-threaded Tokio executor. If you spawn tasks at different priorities, then different priority levels from interrupts, either even if you're using them raw or you're using them through a higher priority executor, different priority levels behave kind of as threats, because you get one kind of priority level that can be preempted at any time, like literally between any pair of instructions by another thread. So how it works is, if it feels a lot like threads, we can use the Rust send sync mechanism. So sending things across priority levels requires send. Sharing pointers across priority levels requires sync. And if you want interior mutability through sync things, you have to like use a mutex, which is a critical section, which will temporarily block interrupts, saying, hey, I want exclusive access to this piece of data. So yeah, it does have an impact, but it's fully safe and fully checked at compile time, the same way standard Linux threads are in Rust. Yeah.
All right, any more questions over there?
Yeah, so is there anything that would be in your fantasy interrupt controller or fantasy hardware platform more general for this kind of?
So most of the work in Embassy has been the hardware abstraction layers, because hardware vendors do really crazy things at sometimes. Like sometimes you can tell, for example, they designed a peripheral to be used only by blocking, and then they bolted interrupts on top, but the interrupts flags work in weird ways, or they magically clear if you do some read, or they even expect you to only do I/O in the interrupt, which is not the case in here, because you use the interrupt just for waking, and then the I/O is done from the task. So I don't have any actual concrete wish list. Like the existing design, like the ARM NVIC interrupt controller is really good. In RISC-V, we could use some more standardization. I don't think I have anything in the wish list, actually. The only thing is, vendors, please don't do weird stuff. Like stick to regular interrupt flags that you manually clear and work the way they should work, and that's it. Yeah.
Yeah, first of all, thanks. We use Embassy, we use Embassy in production, and it's great. It makes our life a lot easier. I am wondering, like, not all of the crates are currently on crates.io, and so we have to use like a Git dependency. Is there anything in particular that you're waiting for before having like a proper release cycle, or maybe a version 1 or something like that?
So all the crates are on crates.io in January. We released 0.1 of everything. Since then, there's not been many changes in the core, so the versions on crates.io are still relevant and they're perfectly fine. On STM32, there's been more changes, so 0.2 release is a bit overdue. So yeah, the plan is to regularly do releases, maybe every few months. But yeah, help is always welcome on that, because like coordinating releases and writing changelogs and blog posts is a bit annoying. So yeah.
Alice over there.
So you said you had mutexes with atomic context-like things. Do you have operations that are unsafe to put inside such atomic contexts?
So the way it works is the atomic. No, so there's atomics, which are the standard core sync atomic.
So I'm thinking you mentioned a mutex,
Yeah.
which prevents interrupts,
Yes.
which reminds me of stuff we're doing in Linux kernel, where we
Yes.
trouble with like while you're in a atomic context or like the critical region of a spin lock, if you call anything that sleeps, that's a problem.
Yeah. So you already get that naturally because while you lock the mutex, you have a closure. So you're already prevented from doing async stuff there. But other than that, no, there's no list of things you're allowed to do or not. Just if you lock a mutex, you have full immutable access to the interior of it, like in a regular Rust mutex. Yeah.
I guess you don't have threads.
No, you don't have threads. Yeah.
All right, any more questions? All right. Then a big thank you to Dario.
Thank you.